and welcome to the Automotive Tech Deep Dive podcast. My name is Sudhi Uppuluri, the CTO of Computational Sciences Experts Group and the host of this podcast, where I explore the science and technology in the automotive industry with the experts, but without the jargons, in simple, plain English, so all of us can understand the nuances of the emerging technology. Take a listen. Jeff, thank you very much for speaking with me today. I've been meaning to talk to you for a while about two-phase systems, refrigerants, AC systems, all of that. And so thanks for meeting with me.
Glad I can help.
A little bit of background about yourself. So you've been working on AC systems at GM for almost all your life.
Almost all my life. I have 39 years at GM, and all but 2 were working in HVAC. So 37 years in the HVAC area.
All right, cool. And I find HVAC systems super fascinating because, as I was saying earlier, it's not intuitive at all. You know, you look at other systems like physical systems, you see them, you see what's happening, and it makes a lot of sense. HVAC systems, on the other hand, you've got to figure out, you have to plot them, figure out the pressures, the enthalpies, the phase of the liquid before you can really figure out what is it that it's doing. Before we jump in, I want to start with refrigerants. So for a long time, we've been using R134A.
Right. Yeah, 134A didn't have any ozone depletion. That was the problem with R12, is it actually attacked the ozone.
Right.
But it was still a greenhouse gas, 1,300 times worse than carbon dioxide, right? So
that's how big the number is?
Yeah.
1,300?
Yeah.
For 134A?
Yeah, 1354, I think is what the number
okay.
is. Yeah.
And one is carbon dioxide, right?
Yes.
So,
right.
Okay.
So it's a definite greenhouse gas. It does not tend to break down very fast, so it has a long atmospheric life and pollutes our greenhouse layer.
Got it. So we're now moving from R134A to 1234YF. So my question is, how did we come up upon a new refrigerant? What is the process? Like, what are we looking at? How do you come up with, do you go one molecule at a time trying to figure out a new work?
There's a number of things you have to look at. One thing is we like to reuse hardware, right? It's nice if you don't have to redo your hardware. So the thing about it is, if you're looking at a new refrigerant, but you can retain the hardware on the compressor, there's an awful lot of tooling to be saved.
Right.
When we were looking at YF, one of the big alternatives was going to CO2, R744.
Right. And Mercedes-Benz is a big proponent of that?
They were a big proponent of that. Now, they've done YF cars too, right? So they're not just a CO2 company now, right? But the bottom line is that R744 is an exceedingly inexpensive chemical. CO2, nobody's got a patent on that one. Right.
Right.
You can buy CO2 relatively inexpensive, even in laboratory grade kind of stuff that you'd want to put into your vehicle.
Yeah.
The problem with them are the operating pressures are so high, you have to design pretty much all new components throughout your AC system. Some of the controls can be carryover,
right?
But that's about it. All the heat exchangers have to be unique.
Yeah.
The compressor has to be unique.
Yeah.
It's a fairly decent refrigerant. If you have a mild climate, it works rather well in Europe. Europe doesn't tend to get above 32 degrees C.
I see.
It tends to be a poor choice for the United States because the United States gets up to 45 degrees C, and you're well into the triple point of CO2. And although it's actually, I mentioned it was an efficient refrigerant, it is if it can stay and under the 30 degree C mark, but once it gets up into the 40 and the 45 degrees C, it's actually on an annualized basis a higher consumption refrigerant than R7 or 1234YF.
Got it.
Your LC, we call this the life cycle climate projection, right? Your LCCP
Right.
that takes into account kind of cradle to grave usage of the energy. Right.
So then are European car makers deciding on CO2 mostly because is their limit just 35C? They go, okay.
Well, take Volkswagen as a for instance. Volkswagen is a little bit more looking at CO2 from a whole vehicle perspective. They didn't fall in love with CO2 like Mercedes did, right? Mercedes really tried to put all their cards in CO2 and try to stop people from using 1, 2, 3, 4 YF even, right? Volkswagen did not take that kind of stance. They simply wanted the best refrigerant, and they use CO2 in Europe. But when that same vehicle, like the Volkswagen ID4, comes to the United States, it's a YF car.
Okay. Isn't that a lot of money, or is that?
It sure seems like it.
I mean, why would you do a CO2 specific car for Europe when you can just do a YF car across the globe?
Across the board. I think you would wonder about that, but I don't know about the politics that go on with these kinds of things with their European partners and the legislator and all that kind of stuff. There's probably reasons they have that maybe I don't understand, but the bottom line is CO2 is a decent refrigerant for the European market. YF is really a better refrigerant of what we have available today for the U.S. market, and they've divided. They figure they have enough volume in each market that they can do separate tooling.
Because it's definitely not the same system. It's like
it's a completely different system.
Right.
Yeah.
I remember 20 years ago going to the European VTMS conference that talked about alternative refrigerants. And the biggest thing that stuck to me was the fact that CO2, because of high pressure, leaked. And so the amount of leakage of CO2 in the AC system was quite high. Is that the primary issue, or it's one of the issues?
I don't think leakage is a big deal anymore. Years ago we developed metal slimline metal washers, right? That crushed metal, and they're very, very good at sealing, even with our manufacturing processes that we use. So I don't think the CO2 leakage is as big of a concern as it was. One of the problems with CO2 is if it leaks into the passenger compartment, you might think, oh, CO2, that's not going to be harmful for people.
Right.
It is. At those concentrations that get into the cabin with a release of, say you get into a crash and your evaporator bursts or something like that, or there's corrosion in the evaporator bursts, right?
I see.
And certainly in Michigan, we do have corrosion issues with evaporators, right? If that evaporator breaks, that CO2 in the passenger compartment has to be measured, and you have to be able to drop the windows and that kind of thing, or the people
lose consciousness.
Don't do well, right?
Right.
CO2 poisoning is not as bad as carbon monoxide, right? Carbon monoxide does put you to sleep. CO2 poisoning, right, tends to give you an excruciating headache, then kill you, right? So it's it's not as pleasant, but at the same time, they're both they cause lack of poor judgment on your part and whatnot, right?
So then, do the European vehicles which have CO2 have a CO2 sensor?
I believe they do. Yes.
Okay.
Yeah.
And then, if it reaches a threshold, some automatic action happens
right
to do that.
Yep. What
is the methodology with which you come up with a new refrigerant? It just
as I mentioned, it's really you look at a couple of things. One thing about CO2 that YF doesn't do well is CO2 is a reasonable heat pump refrigerant.
I see.
YF is not, and why is CO2 better? Well, YF, when you get into this very cold environment, doesn't have pressure anymore.
Mm-hmm.
It actually around I think it's minus 50-ish. Flips around and goes negative in pressure.
Oh, okay.
Right? You have vacuum in your system.
But minus 50 is too low.
But if you're going to be a heat pump, you're going to be removing heat from the environment.
Right.
That means you have to have at least a 10-degree delta T.
Yeah.
So if it's minus 40 out, you're going to have to be
minus 50
in your refrigerant system, right? And that's where YF isn't a really good refrigerant for you because you've lost your mass flow. You don't have enough mass flow anymore because you're only filling the compressor with whatever the suction gas is, right? If that suction pressure is high, you're putting in a lot of mass of refrigerant. You're going to get a lot of mass flow through your system, right? If that pressure is very, very low, very little mass flow. Same volumetric flow, way less mass flow, right? So
couldn't compressors be changed with the design or have multi-stage compression?
Yeah, you can do some things, but they generally have to get big. And that's somewhat problematic, right? And that's one of the reasons why we have the SAE Thermal Management Refrigerant Cooperative Research Project going on, right? To come up with a better heat pump refrigerant than the current YF systems, which have some significant limitations at say -40. Right?
Got it. So it seems to me that we as an industry decided on YF before we realized that heat pumps were going to be a common thing.
Yeah. We worked on that, the YF refrigerant thing. We basically put that into production in 2010. So we were working on that throughout the 2000s, basically coming up with that. And at that time, EVs were real distant on the horizon. We'd done the EV1, right? General Motors knew a little bit about how to put a lead acid vehicle electric on the road. It didn't seem very near that would become mainstream. So it really didn't enter into the equation for 2010. As we look at 2020, it's a very different vision. We understand that there's going to be a substantial amount of EVs on the road. And we have to have heat pumps in those vehicles if we want to make them efficient, right?
So does that mean that heat pumps are going to be a standard across all electric vehicles? What are your thoughts on heat pumps?
Well, you have to remember that we've been having more and more trouble, even with IC engines, finding enough heat. The IC engines have been under tremendous scrutiny to drop their CO2 emissions, to make them more and more efficient.
You mean improve the fuel economy?
Improve the fuel economy, right? I drove a 5,000-pound pickup truck here to this event today, right? It got over 30 miles per gallon. That's unseemingly, but 10-speed transmissions, small diesel powertrains that are turbocharged, right, can really try to squeeze a lot of energy out of a small amount of fuel. And then what that means is that the waste of energy is being reduced greatly. And when you reduce the waste heat, even the IC engines need help now warming customers up. So heat pumps are not just for EVs. As IC engines continue to get more and more efficient, either through hybrid means or diesel means or whatever means that we're going to use to make those more efficient, heat pumps are going to be one of the plays that are going to be needed if we're not going to use, electric heat sources.
And hybrids, that would make a lot of sense because the engine's off a lot of the time. And the goal is to keep the engine off as long as you can. And so you wouldn't want to turn on the engine.
That means no waste heat. That means it's basically, and if you look at the amount of time that they're used, even a hybrid that has maybe 10 miles of range, for a lot of people, that's their commute. Right? So if it's got 10 miles of range, that engine may not run for quite a period of time, right? So it's very important that those vehicles have a heater system that's somewhat efficient so they can get their 10 miles of range and not 6, right? And heat pumps are one way to do that.
Cool. So staying still on refrigerants, tell me more about the cooperative. Like, what is the goal? What are you guys trying to achieve?
The goal is that if you have each manufacturer working on the problem, you're going to come up with some different solutions, but they're not going to result in a new commodity. What you'd like to have is a refrigerant system that's basically close to a commodity, something that the same components are used by all the manufacturers. Right?
Similar to the AC system today.
Right, where we don't have General Motors doesn't have a compressor that they use that no one else uses.
Right.
It's an industry part.
Right.
Right. And we're adopting, General Motors is adopting an industry part, and so is Stellantis and Ford and Toyota and everybody else, and Honda, right? And that's the way it's most economical and the most reliable to have a vehicle, right? Everybody is working to make the reliability better, not just one manufacturer because it's their only part, right? So
right.
It makes a lot of sense to try to develop those commodity parts, right? And that's one of the reasons why you do things like a cooperative research project, is so that you can all consensus on a given direction. It's not like a requirement to use whatever the group decided was the best choice. Somebody still has the right to go do something else, but the incentive is often there to do the same thing, right?
Right, got it. And the goal is just a refrigerant or refrigerant and a two-phase system as well?
Last time around, it was basically a refrigerant when we decided on YF versus R744. There was a cooperative research agreement that went on in the 2008 timeframe as well to do this kind of stuff, right? Yeah. This time around, because heat pumps have some benefits with secondary loop kind of activity,
which is cooling the motors and the battery, or just
we
moving the heat
already
around.
have a secondary loop in the vehicles today, right? Batteries don't like to have direct refrigerant heat exchange, so they tend to like to be cooled with coolant. So we have a chiller, right? That's half of a secondary loop, right? If you look at systems that can utilize a secondary loop, your choices of refrigerant becomes larger.
Because you are not exchanging the heat with
don't have to have the refrigerant enter the cabin.
Right, okay.
Right, today we have refrigerant YF, which is an A2L refrigerant. It's slightly flammable.
Okay.
If you put it in your barbecue grill, you're going to like to have beef tartare, right? You're just not going to like to have cooked meat because it doesn't cook with that refrigerant. Right. It doesn't burn very well. In fact, when it gets discharged with coolant, it generally doesn't create a problem because the coolant can tend to put it out pretty well.
Right.
Even though coolant, you think, coolant's flammable, that's an oil.
Right.
But it's got water in it, and when it comes out as a steam, it takes a lot of energy out of things. Right. Right. So the ability to have flame is greatly reduced. Right. So we have this mildly flammable refrigerant, and we adopted YF at the time because of that characteristic that it was a decent refrigerant for us. It could go into the same. We could use the same compressors as we had with 134A. It had what's called compensating factors. It's heat transfer per unit mass is about 60% of what we had with 134A. Yeah. So you'd say, oh boy, you're going to need a lot bigger compressor. Well, it's also more dense.
Oh, I see.
So those are compensating factors, and they get you back to about 95% of the way there. So you get kind of 95% of the way there with the same components, and then you just work the nuances of that. You put in a internal heat exchanger or something to get that last 5% back. That's basically what's been done with YF. Is most YF vehicles have an internal heat exchanger to make them a little bit more efficient, and we get back to the YF level of performance.
Got it. So so when you said the refrigerant doesn't have to enter the cabin, it means that we can get rid of the evaporator and use just the heater core to do both heating and cooling.
Right. Right.
Okay.
You might, in HVAC, right, we like to have a dehumidification function.
Yeah.
That usually requires two heat exchangers. One heat exchanger to cool it down, remove the humidity, and another heat exchanger to temper the fluid. So you might have two heat exchangers, but they'd both be coolant heat exchangers, right? Right. In a secondary loop. You wouldn't have the refrigerant having to enter the cabin. And like you say, you've already got the chiller for the battery situation. So there's there's ways you can do things to get some synergy in your system now to try to do a secondary in the cabin. What you have to work on a little bit is on the heat pump side. We're using what we call a condensing heater in the cabin now. Right. A condensing cabin in a heater works fine with an A2L, but not with an A2, right? If you use it like a propane in the vehicle, you wouldn't want to have a condensing heater in the cabin. You'd want to have that in a indirect heat exchanger, indirect condenser, if you will, that would take that heat, put it into coolant, and heat the cabin with coolant.
Right. That sounds quite logical, but the systems that I've seen of heat pump today have two heat exchangers. I see a heater core, and then I see a condensing heater as well.
Right. So what you'd have is you would have the condensing heater would come out.
Yeah.
That would be replaced by an indirect condenser, and you'd have another heater core in its place if you wanted to do humidification.
Okay, got it.
If you figured out a way, there's
with electric heaters maybe. So if you
there's ability to use electric heat. There's also the ability to still do dehumidification with one heat exchanger if you control flow rates in the upper and lower halves and that kind of thing. There are things that can be done with one heat exchanger and still be able to do humidification. So I'm not telling you you have to have two, but two's the easiest method, the most straightforward way to do it.
So your cooperative is looking at architectures too, because it matters what the architecture will end up looking like to pick the right refrigerant for it.
Right. We have different teams working in the cooperative research group, right? We have a team entropy. Their main focus is on secondary loop.
Team entropy?
Yes.
What a cool name.
We're all engineers, right?
I love them.
Chris Seaton is leading that team, working on the architecture that would be best suited for a refrigerant like propane, for instance. Right?
Okay.
Keeping it. Propane is actually a very good refrigerant.
Okay.
It has very good density characteristics and pressures. It works really good in a heat pump environment. It's just that you can put that in your barbecue, and you will have well done meat, right? So it's important that that stays out of the cabin, at least as we know it today. With the safety systems we have, we tend to want to keep that outside the cabin, and that means another heat exchanger, if you will, right? Taking that condensing heater and turning it into two heat exchangers, an indirect condenser that takes the heat from the refrigerant, puts it into coolant, and then a cooling core, if you were, or a heater core to transfer that to the passenger compartment.
Got it. So where are you seeing this architecture go to? So where is there a winning architecture emerging for an electric vehicle?
Yeah, it's interesting. There's a lot of synergy possible in a secondary loop that you just don't get with direct heat exchange. At the same time, there's some efficiencies of direct refrigerant to air heat exchange that are beneficial in itself, but they don't have very many integration opportunities. So that's what the team is trying to wrestle with. Is it better to work on a somewhat less efficient heat transfer method, but it integrates into the vehicle oh so much better? Or is it better to work on a direct heat exchange system and forego those integration benefits? I tend to think that over time, because we like simple and things tend to go simple over time, we go from complicated to simple, I think secondary loop is going to be the way, because the way it integrates in with battery management and battery heat transfer management, the way it can store more energy for start-stop kind of operation and things like that. And the way you can do things like warm the battery and warm the people at the same time that you can't necessarily do with the systems that we have today so easily, right?
So let me ask about the other part of the heat pump, which I've heard folks have issue with, which is when in a heat pump mode, you have this condenser in the front of the vehicle, and that is trying to reject heat. And so, as you said, it's very cold outside, minus 30, minus 40, and then you have the condenser at minus 50 with the delta trying to reject it.
Right.
And so you have this problem of frost
Right.
forming on it. How do you see this problem? Do you see it as an unnecessary problem that can be done away by other methods?
Well, first of all, there's an awful lot of heating situations that are above 0 degrees C.
Right.
And if you're above 0 degrees C, it's going to be somewhat difficult to get that heat exchanger to freeze because it doesn't go very deep below a freeze point, right?
Right.
At the ridiculously cold temperatures that you're talking about, even though it's really, really cold, the moisture content in the air is very low.
Right.
There's not much moisture to be had. So if there's not much moisture, it takes a rather long time. There are these situations, though, that are the in-between, say minus 10 degrees C.
Right.
Well, there's
which is one of the fuel economy tests, minus 7.
It is, right. And there's a lot of heat available in the air.
Yeah.
You'd like to be able to pull that heat into your system and use it, but at the same time, there's a lot of moisture in the air, and now you do have to manage the freezing, right? But we don't see it insurmountable. We see that we can, particularly if we have like a secondary loop or something where we can store up a little heat, we can simply reverse the cycle again, warm that heat exchanger, push off the ice, and begin fairly rapidly doing our extraction of heat from the ambient again, right? So,
right. And so is that the approach that some of the car makers are doing, which is cycling the heat pump to shed the frost and then run it back into heat pump mode?
It's not in production yet. It's something that's being looked at. Right.
Got it.
Yep.
How does one detect frost on the condenser?
Usually operating pressures will tell you what's going on because you're looking at a certain mass flow of refrigerant, right?
Yeah.
And if you aren't getting the heat transfer, you have to run the compressor faster now,
right?
Because you have less heat exchanger out there because some of it's covered by ice. That's usually the way you can detect it. I don't know that you're going to need a sensor per se. You're going to look at your compressor speed and decide, am I getting the refrigerant flow that I expect to have, or am I starting to fall off on heat transfer? So
degraded performance
would tell you it's time to.
We just attribute it to frost,
right?
And do that.
Right.
Got it. So the Tesla Model Y has a very, very novel heat pump system.
It most certainly does.
And it doesn't have an external heat condenser, right? It only has a low temp or a coolant heat exchanger.
Right.
And then the condenser.
And an indirect condenser.
Indirect condenser.
Right.
Which in many ways gets rid of the problem.
Well, it doesn't get rid of the problem. You still have to worry about your coolant heat exchanger icing up. But at the same time, you have hot coolant available as well.
Right.
And you can decide to send some out to that heat exchanger to push that ice back off again.
Right.
So it's not that you don't have the hot coolant in the system to be able to do your work. You do. You're sending it to the battery. You're sending it to the passenger compartment. Right. You just need to every once in a while send a little bit to your external condenser.
Right.
And they have that octo valve at Tesla that really lets them direct coolant exactly where it needs to go.
Right. Which I think is more of a manufacturing jiu-jitsu rather than real design stuff.
Because, absolutely. It's a way to try to get your system to look less complicated, right?
Yeah.
If you have 9 valves, it's kind of difficult for a mechanic to get his hands around that. But if you got an octo valve, maybe it's a little easier for him, right?
Pull it out and do that. If you had a coolant that's rejecting or pulling heat from the outside in a heat pump.
Right.
So I'm imagining this Tesla Model Y heat exchanger outside. How would I know my degrading performance? How would I detect the frost?
Well, you're trying to pull. You're trying to get your coolant to pull heat into your system.
Right.
And it's the same thing, right? Is that you're going to be looking at your suction pressures, and when they start to drop, it's because you're not getting as much heat pulled from the ambient any longer, right?
Oh, right.
So it's still going to be...
You're still looking at the compressor.
Right. Right. But instead of looking at, what's going on the high side, you could probably be looking at the low side more, right? So.
Right. So going back to then refrigerants, how many candidates you have? 5, 10, 3?
It tends to be less than 10. There are a number of blends that we're looking at again. There was a big study, a CRP, to look at blends a few years back, right? In the 2005 timeframe, right after we understood how expensive YF refrigerant was going to be. There was a big push to do some blends. Turns out those had patent issues too, so they didn't go very far, even though they were fairly efficient. Now we're looking at some blends that are kind of free of those patents, that don't have the YF in them to the same degree, right? And there's a number of those. It's tricky to do a blend, because if you want the best heat pump refrigerant, you're generally going to come up against the global warming potential number, right? European Union has stated they want refrigerants at 150 GWP or less. They have the global warming potential of no more than 150 times what CO2 has, right?
What do you think of that regulation? Does it seem arbitrary?
It's short-sighted in that LCCP, right, the life cycle climate performance of a refrigerant, takes into account that characteristics, as well as how much CO2 does it take to make the heating and cooling, as well as what does it take to manufacture and recycle and cradle to grave kind of stuff. So LCCP is a much more robust way to look at it, but it's too complicated for a policymaker, right? Policymakers have to keep things a little simpler. They're not engineers necessarily. Some of them are, but GWP is as far as they've been willing to go in the past, right? But at the same time, if we had a refrigerant that, say, is 200 GWP, but it's got the absolute best life cycle climate performance of anybody else, and it's maybe 30% better than its nearest competitor, I think we could take on that political challenge and get that refrigerant accepted, right? Particularly in a system that has very low leak, that we recycle, et cetera, right? We don't have one of those yet. So it's not like we're looking at these GWPs of 200, right? So we're looking at, GWPs between, 1.5 and 150. And the best refrigerants tend to be up towards the 150. They're not going to be necessarily the best political favorites. They're really going to have to show their benefit in LCCP to really make it worthwhile, right? Outside of the cooperative research.
LCCP just European regulation only?
No, that's basically.
Oh, I'm sorry, no, not LCCP. The GWP 150.
The GWP is a European unique regulation. Yes.
What about North America?
North America, we use this safe snap ruling kind of a thing, right? And they take into account a little more than just GWP. They do take into account LCCP and that kind of thing, right? LCCP is one of the reasons why we were able to get YF on the SNAP approved list, right, as opposed to say CO2 or 152A or whatever, right? So
because it was really pushing at the closer to the 150 mark.
It was, well, no, YF is very, very good. I think it's I don't remember the exact. I think it's somewhere around 1.5, right? It's a very good global warming refrigerant, but it also had a decent LCCP number too, right?
Got it.
So it became easier to adopt, right?
Got it. So so going back to the question of what are the refrigerants on the short list, are you able to talk about some of the good candidates?
Cora is doing one called, they call it Beyond 744, right? It is it's taking CO2 refrigerant, which we know is kind of a good heat pump refrigerant. It just tends to have a problem for AC in hot operation. Right. they're looking at blending that slightly to try to get that side better and accept this refrigerant that's already a good heat pump now as to be more efficient for AC, right? That's an interesting system, especially for users that already have high pressure in their system, right?
Right.
The Europeans that run CO2 would love to have a beyond
CO2. Is it another refrigerant that works well in the same pressures as CO2?
Yes. Yeah. And there's a Team Entropy, of course, is working with propane, which is very interesting. And then there's a number of other manufacturers that have come up with blends that are also interesting. The blends would tend to go into direct expansion systems a little better. So if you didn't want to put in secondary loop, they would tend to be a better shoe-in for you.
Right.
And they're non-flammable typically, but they typically have some limitations in performance. And like I say, the best ones from a heat pump perspective tend to be a little higher in GWP than the ones that don't. Right. So,
but secondary loop is here to stay, I think. I mean, just like EVs, you think are here to stay.
Right.
I mean, we don't sell very many EVs right now. It's probably only single-digit percentages.
Right.
And most of the money is still made from SUVs and pickup trucks.
Right. One of the things about secondary loop that makes it so interesting for engineers is the refrigeration system tends to implode on itself. Right now you have a compressor, and up front you have a condenser.
Right.
Maybe in the passenger compartment you have a second condenser, and then you have an evaporator.
Right.
And it's a distributed system.
Right.
When you have a secondary loop, the refrigerant is exchanging heat with coolant. You can have the compressor tagged onto the side of it, an indirect compressor exchanging heat with coolant, and tagged onto the other side of it, a chiller exchanging heat from refrigerant to coolant. And this little device now can be a commodity.
Yeah.
You could have 3 sizes fit everybody in the automotive scheme. Sometimes people are going to need more than that. Maybe they use 2 small ones, but it becomes a commodity, right? A dorm refrigerator is a commodity.
Right.
You pay less than $100 for a dorm refrigerator because they sell so many of them and they're all the same, right? They run the same systems. This little indirect compressor system could in fact have some pretty good economics just because of that commodity kind of pricing that would come about because this same piece of hardware might fit many different cars.
Plus, I see a lot of savings in terms of assembly and all of that, because right now the AC system, as you were talking about, it's a sprawling network.
We have this.
Turns it into
we
a box.
have a tank farm in a plant. An assembly plant has a tank farm
Yeah.
to have the refrigerant system that they have to charge the car with. It's a fairly elaborate process.
Right.
They have to charge a car within 60 seconds and whatnot. It's fairly detailed. This little commodity would come in charged.
Right. You just bolt it in.
You
and
bolt it in and go. Right. It would
would
change the game in manufacturing. And that's one of the integration areas that I'm talking about, right? That integration may overwhelm any little efficiency differences that we may have. And the integration might be so good with this system that, the cost and the reliability and the manufacturing hours might get so good that you say, okay, I'll forego the 5% efficiency difference, right?
Right. Makes a lot of sense. Yeah. So is that what the cooperative sees as the direction for the architecture?
I can't speak for the whole cooperative. I think there are people in the cooperative that feel that way, and I think there are people that don't feel that way.
What group are you in? Are you in the black box group, or are you
I have high hope for the secondary system. I really like the idea of getting everybody to use the same components, right?
Yeah.
And when you can make the components smaller so they can just hop from one platform to another, the chances for reuse are just much, greatly improved, right? So
Right. Agreed. So, wow. And I think this kind of feeds into what I was going to ask you about what what the future of the system would look like. So if I were to take Jeff, put him in 2035, 15 years forward, not so far forward that it's going to be the Jetsons' future, but far enough forward that the little kinks and little give and takes have been settled in. And I open a people's car, a Volkswagen Golf, e-Golf. What would you see in the thermal management system?
Yeah, I think it's likely for me that we're going to be into a secondary loop system. So the refrigerant system is most likely going to be able to use any refrigerant that we want because it's a small mass of refrigerant and it doesn't enter the passenger compartment.
Right.
So it gives us a full complement of refrigerants. We don't have to worry even so much about global warming potential, perhaps because we can be hermetically sealed now.
Right.
We don't have any rubber hoses and that kind of thing.
You could use propane, your favorite.
There's options, right?
Right.
The moisture ingression into the system and all that has been greatly reduced because we don't have to have rubber components. It's very interesting, the simplicity I think that would come about from such a system. And for that reason, I think it's likely to be the choice as we move forward. Just a lot of integration situations with battery warming. Some of our vehicles might have fuel cells. It'll integrate into those better. I think it's likely to be the favorite just because of that. It's premature to put all the eggs in the basket, because we are still doing tests. We're still revising our efficiency tests, right? Our J7 or 2765 is the test we use today to measure AC efficiency. We're expanding the ambient range down into the heat pump category so we can measure the efficiencies in the heat pump range as well and come up with an overall impact of efficiency. And then, of course, we can put that into our LCCP and be able to understand the life cycle impact of it, right? But I suspect once we get that done, as long as the secondary loop doesn't fall on its butt in those areas, I think it's going to be an overwhelming favorite, right? If it can kind of play in the same range as the other refrigerants, but has all these integration advantages,
right? It
seems to me that's going to be the likely scenario.
So the picture you're painting is you look at the thermal management system and you have this compact two-phase system in the middle that either provides cooling or heating depending on what.
Has hot coolant, has cold coolant coming out of it. Right?
And then you get to pick.
You got you got these valves that are sending it all to the right spot, right?
Yep.
But you don't have to worry about refrigerant leakage because it's been hydrogen leak checked and all that kind of stuff at the assembly location. You don't really care what the refrigerant is in anymore.
Yeah.
Because you're not interacting with it. If it's giving you the right output of kilowatts on each side, you're going to be pretty happy camper, right? So,
what about phase change materials? Would you think we'll see technologies related to phase change materials?
A battery in a vehicle is tremendous mass.
Thermal inertia.
They're very heavy, and they have tremendous thermal inertia too. It's hard to imagine you would need more thermal inertia than the battery could offer you, right? They are a tremendous holder of thermal energy, right?
Yeah.
And I think making use of that thermal energy the best you can is a very wise thing to do, right?
Yeah.
Before you have an iced up heat exchanger, if you spent some time warming the battery before that heat exchanger iced up, when you switch off that heat exchanger to de-ice it, you simply start pulling heat from your battery. Right? It's an easy transition methodology, right? So.
Right. Let's move from under the hood and thermal management to the cabin side, and that's the other side you've been involved quite a bit as well, cabin comfort. Let me start off with the defrost requirement, because that's one of the things that always bothered me and wanted to ask you.
Right.
Which is, there's this defrost requirement by NHTSA that says that the windshield needs to be defrosted by this percentage by this time,
Right.
by 20 minutes or something, and then this percentage by this time,
Right.
And there is a lot of bending over backward that happens to meet this defrost requirement in terms of hitting temperature profiles and all of that.
Right.
What do you think of that?
Well, there's two things about that. It's a 1964 law. It was edited in 1967, basically to correct a few errors, right, that were existing in the document. So it's still basically a 1964 law. It applied to passenger cars.
Right.
SUVs are not cars.
Yep.
Pickup trucks are not cars.
In what sense? In cabin size or
They don't have to meet a law written for cars.
Oh. Okay.
That law is written, if you read it, it says a car must meet these clearing requirements, and a truck must have a defroster system.
That's it.
Period.
Like checkbox.
Right. So most of the vehicles built today do not have to meet that requirement. Now, customer satisfaction comes into play, and I don't think you'll find vehicles that drift very far from that formula, because that is in fact what customers expect in defrosting performance, right? So most vehicles I think you'll find do meet that, but by letter of the law, it's not an FDM-SS that applies to a pickup truck or to an SUV. It only applies to cars.
Does it still apply to cars, or is there?
It still applies to cars. If you have a hatchback, maybe not. But if you don't, if you have a trunk, you're going to need to meet MVSS.
And what do you think of that requirement for it?
It's
it is still 1964, pretty antiquated, I guess.
Pretty antiquated. It doesn't really meet the area that customers are concerned with. Customers are really concerned with freezing rain.
Right.
Freezing rain comes really close to 0 degrees C, maybe 5 degrees C, right? That's the area where ice can be very thick and an impedance to the vehicle safety, right? So most manufacturers work really hard to make sure that's not a problem at minus 5 C.
Is that the problem that's trying to address? Which is, I thought that the problem it was trying to address is first thing in the morning. I mean, that's the biggest problem for me, which is first thing in the morning, I'm going to work and I've got this 20 minutes of scraping that I have to do.
Yeah. The thing is, though, that scraping tends to be more common at minus 5 than it is at minus 20, just because it's minus 5 more commonly than minus 20.
Yeah.
And further, at minus 20, there's not a lot of moisture in the air. Right. So it's a very thin layer. And the way the test is written, too, is that test at minus 18, because it was written for 0 degree F, right? We didn't know about the metric system, I guess, in 1964, although we did. It has a very thin layer of ice that goes on.
Right.
And it's very difficult to even do the test because that layer of ice is so thin that your brush strokes that overlap can tend to give you a different result every time you run it.
Right.
It's a very difficult test to run. But if you run a good test, it is still hard to meet because, in fact, the ambient is so low that the engine takes longer to warm up. Right. And it does generally take a decent amount of kilowatts of heat rejection to melt that ice just because of the ambient, right? The problem is more testing it is problematic because of the repeatability of the test. Testing at, say, minus 5 or that range, much easier test. You put in a much thicker layer of ice. There's not the test variation. And you need about the same amount of heat, by the way, right, to clear both sets of ice. But we really think the customer is better served by the higher temperature test than the minus 18 test, just because it's not minus 18 very often, and it's minus 10 or minus 5 very often.
Yeah.
Right?
So in the future vehicle of 2035, would I see would I see like a heated windshield, or would you still have the same kind of defrost method?
It's interesting. There's a lot of technology to help passengers get warm, right? If you want to warm up passengers the most efficient way, you treat them as like they're kind of in a space suit.
Yeah.
You do localized cooling sources, right? Or localized heating sources. The heated seat is a wonderful device. When a person sits in a car on a heated seat, they pretty much cover every bit of wire in that seat.
Oh,
all that heat is pretty much going into the body.
Right.
It is not escaping into the passenger compartment.
Right.
Heated seats do a really good job of warming people. They don't tend to do beans for melting ice on a windshield.
Oh, because
they're putting all the heat into the people, right?
Right.
And the people aren't radiating at a very high rate to that windshield. They are radiating to the windshield. That's one of the reasons why we need heater systems, is because, the human body's at 33 C. The windshield might be at, 0 C or below.
Yeah.
Pretty good delta T for radiation, right?
Well, what I'm imagining is is how we have it in the rear windshield today. We have heated.
We have a grid. Right.
Perhaps something similar.
There are films being developed to put in windshields to be able to electrically heat the glass. It's not tremendously efficient in that, yes, it's good at getting all the heat into the glass. The problem is, if you put heat into the glass, that heat is going to be taken away to the ambient.
Oh, right.
Making warm glass means that air is just leaving the passenger compartment. So, and then you have to modulate. Now you have to modulate the heat down, just warm it enough not to get the ice buildup, right? That's a tough control system. A lot of these films, as you try to drop the power to them, they don't work very well. They just kind of clear the ice at the corners. Right? So you have to come up with some control schemes on these electric heated windshields to try to do the same kind of thing we do at the rear window. We pulse the rear window wiper, right? The grid, right? We run it steady, then we pulse it to keep the ice away or the fog away, right? Same thing would have to be developed in the front, but these films don't tend to behave as well as a grid system when you drop the power.
Right. So you're not bullish about that technology.
Yeah, I think they're great for the initial clearing, but I think you're going to want to have a defroster duct for kind of the down the road stuff to prevent it from coming back.
Yeah.
It's interesting. It really lets you focus on individual comfort now and not heat people that aren't in the seats, right? If there's nobody in the back seat, you don't want to send a whole bunch of heat back there, that kind of thing. It really helps with that, the localized thing, but it doesn't fare well for keeping the glass clear. So I think the defrost duct. The other thing the defrost duct does too is you can't have a tremendous difference between an occupied and unoccupied seat in temperature anyway.
Yeah.
The car tends to like to brake and accelerate and turn. It doesn't do any of those things in a wind tunnel, but it does do those things in the real world.
Right.
Most of our customers drive in the real world, not in the wind tunnel. So we have to take that into account.
So how does that affect? You mean the hot and cold air inertia moving around?
Yes, I'll give you an example.
I did not realize it was that big of a deal.
In cars today, most cars have rear seat heater ducts.
Yeah.
You might wonder, why do they have rear seat heater ducts? Most of the time, 75% of the time, only a driver's in the car. Why do you need a rear seat heater duct? It's to keep the driver warm.
No.
When the driver slows down, or the car slows down, right? There's a stoplight ahead, right? That cold air, which is laying on the floor in the back seat because it's dense and cold, wants to come rushing forward under the seat. And now all of a sudden this driver, who was feeling quite comfortable because the front heater ducts were warming his environment, all of a sudden can't maintain his desired temperature. He's got to turn it up. That's unacceptable, to be distracting the driver in that way, right? There's a lot of things that distract drivers. We don't need thermal to be one of them.
Right.
So vehicles today use rear seat heater ducts to keep that temperature constant for the driver, so that air in the floor in the back seat isn't so silly cold and doesn't come in and mix, right? But it's for the same reason when we talk about these, airflow based on occupancy kind of systems.
Yeah.
Toyota causes theirs S-Cool or something like that, where we try to do less airflow to unoccupied zones. It's never zero airflow to unoccupied zones.
Right.
It's less because we can't handle a big temperature difference.
Right.
Right. We can maybe handle 5C between occupied and unoccupied. We just can't handle a 20C difference or something, because the car's going to turn, that air's going to mix, and all of a sudden the driver's not going to be comfortable anymore. Right. So,
right. Wow.
And for that reason, I kind of think you're going to need a defroster duct anyway.
Right.
Just to keep the interior from being so very stratified. Right.
Stratified, I thought, was a technology that people were moving towards, or I saw a paper from one of the Japanese OEMs where they were trying to improve fuel economy and say, well, if we want to keep the heat just around the driver. But you're saying that was in some way short-sighted, because you're going to create a big delta.
You can do it within some limits. But like I say, if you get more than, say, 5 or 10C differential between zones, as soon as you turn or brake,
you have a cold splash of air coming in,
and customers aren't going to accept that. Right? They don't accept that distraction. Right? They want their system to be like a home where they walk from room to room and it doesn't change. Right? They want that constant temperature. It's very important to a customer. So yeah, you can. There are some energy saving things you can do with heated seats and slightly reduced cabin temperatures and that kind of thing, but you can't handle just large amounts of stratification, right?
Got it.
You would love to be able to say, let's keep the air close to ambient everywhere, except at the driver. So now those windows aren't losing heat to the environment and the back's not losing heat to the environment. Only the driver's side window maybe is doing that, right?
Yeah.
So the losses go way down. That only works in a wind tunnel. And as soon as you try to drive it on the road, you figure out that, now this is distracting.
Okay. So what technologies excite you about cabin comfort?
I do think even under these limitations, there's a lot of gains to be had with localized cooling. The heated seat, the cooled seat are two big technologies. When you get into a hot car that's been soaked in the summer and that vehicle has a ventilated seat into it, what that means is you sit in the car that doesn't have a treated seat.
Right.
Your body's at 33C, that seat's at 40. You've completely enveloped the seat.
Yeah.
It can't exchange heat with anything but you.
Right.
You've got to take that seat and cool it down. And how are you going to do that? You're going to perspire.
Right.
Your back's going to perspire. Your chest is going to perspire. You're going to have to perspire because your body has to get that seat down to 33C, or you're constantly gaining heat from it, right? Yeah. So what you're looking for then is a kind of a low mass seat. You do a low mass seat and it doesn't work very good for driving dynamics. You tend to bounce a lot, right? So that's not necessarily the answer. Well, if you ventilate a seat, what you've done is you've put this insulation layer between the occupant and the seat and the mass of the seat. Well, if you look at it, cabbies used to run these wood beads.
Right. Yes.
It's the same thing. It's an insulation layer. Right. When you get into a hot car, you're not trying to cool the seat. You're trying to get this top surface of a wood bead down, and the wood bead doesn't transfer heat worth a darn. Yeah. So it comes to your body temperature really fast, and you're good, right? The ventilated seat trying to do the same thing, right? Trying to insulate you from that seat so that the cabin air is kind of going through this mesh layer, right? And ejecting. And it's meaning that your body now can be neutral very quick, right? Where it's not necessarily exchanging heat with the ambient anymore. We don't like to do a lot of cooling with a seat. The body, the big muscle groups in your back and stuff, they don't like to be cooled. They tend to stiffen up. And there are people that run heated seat year round already because they like that sensation of warmth in their back, right, for those big muscle groups. So we can't do a lot of cooling, but there's some experts like Gentherm, right, that really know human physiology and know how to do cooling and not overcool you.
Just the right amount.
Just the right amount. What you tend to want to do is you want to cool the spine, and you don't want to cool outside of that. You want to leave that alone. And in the seat, you've got so much contact pressure with the seat, you generally can't cool anything down there, or you make the person feel wet.
Oh, yes.
Right? And wet does not equal comfort. So ventilating the cushion, ventilating the sides of the seat, and then cooling along the spine really tends to be a very efficient way to be able to get some cooling done for a person and not have it distract them. Right along the spine, there's a lot of blood flow anyway. Yeah. So you can do a good heat exchange with the person, and it tends to work fairly well.
Yeah. These heated and cooling seats or ventilator seats are getting pretty much standard in most of the vehicles today, aren't they?
Especially with EVs, right?
Yes.
EVs want to be more efficient. They tend to have these features, right?
And premium vehicles.
And premium vehicles, right?
Any other particular technologies? Any localized cooling or?
The other localized thing that people are working on is radiant heaters. You see them in Burger Kings, right? They warm burgers with radiant heaters.
Or in the house too.
In the house too, radiant heaters. Radiant heaters in a car, you can get pretty close to a person. Yeah. You have some good, radiation tends to be a distant function of distance, and you can get fairly close. One of the problems is people like to have sunroofs in their cars. And that's really where you'd like to have a radiant heater.
Like right up at the top.
Right at the top, right?
How about up in the front?
At the header is not a bad spot. You have to worry about sun visors and things like that, but there are some opportunities, I think, up at the header region. Yeah. So I think radiant does have a place. It can tend to be fairly efficient because once again, you're not trying to warm the car; you're trying to warm the people. Person. Yeah. And that can go hand in hand with a treated seat, right? And the other device that you can look at is just trying to get the air conditioning vents a little closer to the people, right? If you can figure out ways to get them closer, one of the concepts is, trying to get conditioned air into the seat. And particularly for a driver, drivers drive around with their arms outstretched, right? Right at the seatbelt buckle, right? Back here in the corners is a great spot for an AC outlet.
It is.
It blows right up the side of the occupant and feels very euphoric for the driver, right? He's not bothered by that at all, the fact that he's not sweating. It tends to make him happy or her happy, right? So that's an interesting concept. And I think as we get a little bit more energy efficient, you'll start to see some things like that, right? Seat-centric solutions that really focus on that ability for the seat to be really, really close to the occupant and can do a job a little more efficiently than trying to use the beachfront real estate of that IP, right? So,
cool. Jeff, that was a fantastic deep dive conversation about thermal management, EVs, and cabin comfort. I enjoyed that conversation. We ought to have someone from the cooperative, maybe yourself, come and share all this at the conference perhaps next year.
I think that would be a very good idea.
Cool. Yep. Jeff, great. Thanks for talking with me.
Thank you, Sudhi.
Cool.